Well, good morning, everyone. It's about time, so I'm going to start. My name is Steve Gordon. I'm the current chair of the SIGHPC Education Chapter. This is our second online meeting. Uh, with us today are a couple of the other members of the board, David Halstead um, and Deborah Schwartz. They may be piping in later when we get to questions and answers. So the purpose of today's meeting is to uh, begin reviewing some of the opportunities for education in high performance computing and computational science. Um, and so I'm going to be giving a short presentation followed by questions and answers, and we'll hopefully uh, have some interaction with you through the question and answer screens. So let me start by just talking a little bit about the logistics here. Um, there is a question button from the Hangouts on Air to pose a question at any time. We'll collect the questions throughout the talk and try to provide answers to all the major questions at that time. Please note that there are time delays between requests and replies because of the technology, and in fact the transmission is about a 25 to 45-second delay between when I say something and when you receive it because of the technology. So keep that in mind, but we'll do our best to answer all questions. The entire session is recorded and will be available on YouTube. The slides are actually posted now on the chapter website, which you can see here, which is sighpceducation.acm.org. Under events, we have a link to the meetings. This is where we'll also post future meetings, slides from the meetings, and any other follow-up notes will be on that page. So you can always go back and review things and see the presentation or follow the links that we have through various talks. Today's agenda is really to focus on an overview of academic programs in computational and data sciences. And so what I hope to do is to provide a summary of the number and types of programs, the competencies that are embedded in a number of programs to give you an overview of those, provide specific examples of different program types, although they're, as we'll see, they're quite variant in their structure and what they do, but they do have many things in common. And then we'll bring up some issues with program implementation and maintenance as well. So that's really the agenda for today. And in future, by the way, as you pose questions, we'll also be glad to accept your ideas of topics for future meetings, so you can post them to the question area, or feel free to send me an email with any of those suggestions. The information sources for the academic programs is provided by culling of various lists provided by SIAM and others. We then did an internet search for programs because we found that those lists were not very complete. We tried to do at least a cursory analysis of program websites, and of course, since the data come from the internet, we know that they're completely reliable. So that's with tongue-in-cheek, as we know that that may not be the case, but this is sort of the best we can do. The full listing is available on the HBC University website. I have the link here, and I'll show that at the end of the presentation, so you can have access to that list. We know it's incomplete, so that if you know of other programs that we've missed, or if some of the programs we've posted have a web presence but actually no longer exist or something like that, please let us know so that we can update the list accordingly. Here's just an overview of programs. So we're much better at finding U.S. domestic programs than foreign ones, because many of the foreign ones, of course, are not translated into English. so that I'm sure we have an undercount of foreign programs, but in our list we have 140 domestic programs and 51 foreign programs, for a total of 191 that we found altogether. So there is a significant academic presence for computational science related programs. Of those, the majority are graduate programs, 157, with 34 undergraduate programs. So this is potentially a problem that we'll talk about a little bit later, because we're not really filling the pipeline to graduate programs very well, and that's one of the issues in making these programs viable in the long run. Let me talk first about undergraduate program characteristics. There are 12 programs that we found that have majors in one or more aspects of computational science. So these are full Bachelor of Science degrees or tag degrees of various kinds that have the usual mix of general education requirements and all the things that go along with a bachelor's degree, plus some number of credit hours in a major that's called computational science. The nature of the courses in computational science are very similar to those in the minor programs, which I'll talk about in a few minutes. There are 20 minor programs. They vary in their scope. The mean number of undergraduate credit hours is around 19, where 18 is the most typical number of credit hours. So this is a program where you would take 18 credit hours on top of your other degree program. At some institutions, you're allowed to double count some courses in the minor up to some limit, so you might not have 18 that you have to take as extra. It might be 8 or 10 or something like that, because you're taking those other courses as part of the major as well, because there are overlaps between the major and minor. There are some programs that are called concentrations, and those have smaller number of credit hours, generally 12, and then there's some that are more extensive, and so the maximum number we found was 28 credit hours. There's a wide range of names of these programs depending on the institution. This is sort of a simplistic summary. Two that are called something related to applied math, two that are focused on bioinformatics or computational biology, 3 in computational physics, 2 in computational engineering. The vast majority are just called computational science and are given as interdisciplinary kinds of programs. There's one that's called computational thinking, and there are 3 that are called data sciences and 1 called scientific computing. I should note that in data sciences we only captured a few of these that are related to data sciences related to the sciences and engineering. We did not count those that are related to business. So this is a vast undercount of data science degrees because of that. And in the future, we may try to add those programs and distinguish between the ones that focus on science and engineering and the one that focus more on business applications of data. All the programs require some mix of computer science, mathematics, and 1 or more domain sciences. So they have that in common. The mix of those varies by program type and by each institution. One way of looking at these is by a set of competencies that we developed as part of several NSF grants, and we've done further work with the community to help sort of guide program development. And I'll try to make a link to those now, and hopefully we will get there. So I'm at the HBC University site now. Hopefully you're seeing that. And you can see we have undergraduate level competencies and graduate level competencies, as well as basic and advanced data-driven science competencies. So I'm just going to look at the undergraduate ones now, but you can go back and look at the others later at your leisure. The competencies that seem to be common and are reflected in the courses of the minor programs and the majors really fall into these subject areas: simulation and modeling, programming and algorithms, several mathematics topics, differential equations, numerical methods, optimization, parallel programming, and visualization. The way we develop these competencies, we try to be very specific by having a set of very specific objectives, and then under each of those objectives, a set of descriptors which explain what would be the content of a course. So, for example, if we look at the explain the role of modeling in science and engineering, this would have to do with what, why do people use modeling and simulation, and a course that does that would look at the history of modeling, some of the cost effectiveness associated with doing modeling, why industry uses it to help get things out faster, getting into some of the terms associated with modeling in science and engineering, thinking about validation. And when I teach a course in this area, for example, we actually have the students, we give them a list of examples of how modeling and simulation has been used to create a product, make a scientific discovery, and make them do a little summary of that as far as their experience in the class. So under each of these headings, then, are these descriptors, and they are set out for all of these things. And the reason we did this is because everybody who's thinking about creating an academic program does so in the context of their own courses, and their courses may cross over these categories. So the idea of doing a competency-based program is thinking about what do we have to get into the curriculum somewhere, so that we don't have to create all new courses to make a program that is feasible at our institutions. We may just revise some of the things in existing courses, and that makes it easier to start a course. So as you can see, then these are very similar in structure for the graduate level competencies, which aren't as detailed at this stage, but they at least get at some of the technical competencies in scientific computing and high performance computing, and then the ones that we have in data-driven competencies try to scope out what are some of the core areas in data-driven programs, and how would you present those, and what examples would you use. So again, these are too detailed to go over today, but I leave those with you as a way of thinking about what's embedded in these academic programs. So as I move on to graduate programs, there are a number of programs in computational science and scientific computing, about 20 that sort of have that sort of broad scope, that are interdisciplinary across multiple science and engineering domains. The next highest number of programs is in computational engineering, so that they focus entirely on engineering-related questions in computational science. And then there are a wide range of other programs that focus on specific domains, whether that's bioinformatics or material science or something very specific. So it's very difficult to summarize in just a couple of slides. We'll go back and look at the list of those programs in a little bit. So I thought it might be useful to present a few example programs, ones that I know of because I've worked with them in one way or another, so that I know a bit more about the details. But they are representative of different kinds of institutions. So Ohio State University, a large comprehensive research university, has a minor in computational science. They also have one in computational engineering. It's 18 credit hours. The core courses really focus on those competencies that I talked about just a minute ago. There's a simulation and modeling requirement, a programming and algorithm one, a numerical methods, and then a capstone research or internship experience. Now in the simulation and modeling, there actually is a choice of an introductory course or domain-specific options. This is quite important. So for example, there are courses in simulation modeling embedded in engineering and in a couple of other disciplines which would meet this, this requirement, but for some of the arts and sciences majors there isn't such a course, and so we actually had to come to agreement that in this case computer science would actually teach a introductory modeling course which overlapped with some of the programming and algorithms things that would not require a lot of prerequisites, and that's one of the problems with these kinds of interdisciplinary programs is internal prerequisites, which I'll talk about more in a little bit. Again, the programming and algorithms, we had to come to a compromise for a programming course for non-computer science majors. Of course, if you're taking the minor as a computer science major, this would be covered by your regular curriculum. And in numerical methods, there's the choice of math and engineering courses that cover this material. Because OSU is a large institution, there are many disciplines that have experts in an expertise in computational science, and so this is a list of most but not all of the elective courses in the OSU minor, and you can see it goes across a wide range of fields from computer science, bioinformatics, computational chemistry, mathematics, computational linguistics, experimental economics, geography. I think there's also a geology one which I didn't list, and so on. So this is very comprehensive, and is something that, of course, that couldn't be launched at a smaller institution because they don't have the faculty expertise in all of these sub areas of computational science. But it does give majors from a wide range of majors access to learning about computational science at Ohio State. The next one I'm going to talk about is from Capital University, and this is representative of many liberal arts colleges that have some expertise in computational science and want to do something like this. Their course requirements require 21 credit hours. The core courses are similar to what I noted at Ohio State, but a little bit narrower in focus. So there's an introduction to computer science, which is sort of a combination of a modeling and programming course. There's a mathematics requirement, and so for their biology majors, they actually have a special course to get them into calculus and modeling because they tend to come with weaker mathematics backgrounds. Computational Science 1, which is more modeling and simulation. You see the differential equations and dynamical systems, computational and numerical methods, and they also have a research experience requirement. They tend to have electives then in a few areas that they have expertise, and so they have expertise in neuroscience and psychology, biology, chemistry, environmental science, and physics. So not quite the wide range that you would see at a larger institution like Ohio State, but still a significant, they can draw from a significant number of different majors for this minor. The last example I'll cite is one of a data sciences minor, and this was started about a year ago at the University of Mary Washington in Virginia. It's a different focus because it is focusing on data science. So required courses include Introduction to Statistics, Linear Algebra, a Computer Science 1, Data Mining, and a Modeling and Simulation course. Then they have electives that go deeper into either the data management kinds of things, so data structures, or deeper into the analytics and also parallel processing. So that's a newer kind of invention. There are not very many of these kinds of undergraduate minors in data sciences. Most of the data science programs are either emerging as majors that overlap with business and other fields, or as graduate programs. So the last things I want to focus on are program organization and some of the relevant questions about program success. It's difficult to tell the administrative arrangements in very detail from the websites, but generally they seem to fall into two major groups. So one group is interdepartmental agreements to teach courses and share students and credit hours. So the minor program or even the graduate programs may not have a single sponsoring department, but it's a matter of interdepartmental agreements that have been reached on which core courses to teach, who teaches them, or whether they're shared across disciplines, and then elective courses that are specialties in those particular disciplinary areas. The second arrangement is to have a lead or dedicated department that controls the core courses and then of course the relevant instructional resources in one place. They still will have electives in other domains, but they have a more complete control over the core courses because there is a lead department that's been given those resources to run the program. And those are very different things. Which one works? They both can work. Obviously, making interdepartmental arrangements and agreements at the university can be an arduous task, may take a long time, as the faculty there are focused on their disciplinary responsibilities. At the same time, it may be also difficult to create a lead department amongst who's best among equals to run a program. But once somebody has that lead, there may be an advantage by having the financial resources dedicated to the program over time, and so that may create a more stable environment in the long run, but there's really no data to support either at this stage, but certainly something worth looking at in the long term. So there's several issues then that arise from these organizational things. One is issues of financial resources for interdisciplinary programs. Financial resources have to do with teaching loads and all kinds of things at the university. If an institution has limited faculty with a limited number of faculty with expertise in a particular area, that means that those faculty may be overburdened to teach courses in computational science. They may not have the resources to provide TAs and those kinds of things to give those faculty some relief in their burden. So that becomes an issue in many interdisciplinary programs, not just in computational science, but in general. Another issue that comes up often is disciplinary course prerequisites. As I mentioned in the Ohio State example, we had to come to some agreement that some of the specialized disciplines like computer science would teach a course that didn't require the same expertise and all the prerequisites of their courses for majors. So that often can become a difficult thing to negotiate with the relevant departments so that people can take these elective courses without so many prerequisites that it makes it difficult for a student to get through them. A third thing I wanted to mention as a problem is, because these are not integrated into the regular curriculum, they tend to be add-ons except for the few that are majors. You get a set of students that don't mind taking the extra credit. That as anecdotally, for example, faculty have told me that they recruited a number of students to a minor program. They know that the minor program would give them additional expertise, prepare them better for graduate school, etc. But they're really trying to get through their major with a minimum number of credit hours, both for financial and time reasons. And so you limit the number of students that will take the minor as a result of this, and this becomes a difficult thing in order to maintain class sizes in some of these programs. So that continues to be a problem. In the long run, the obvious solution is that these kinds of expertise need to be integrated into the regular curriculum, but academic institutions change very slowly, and so it'll take some time for that to happen. So that becomes a continuing issue. The final thing I want to mention for both undergraduate and graduate programs is something that we're not very good at in academia, and that is marketing. So even though the faculty know that that there are jobs for people that have this kind of expertise, that this is going to enhance their careers, that it's going to prepare them for graduate research or many other things, they're not very good at getting that across to students. Computational science is something that students may never have heard of. It's not a field that the Department of Labor keeps track of, so that parents who are worried about whether their kids are going to get jobs after they graduate need educating as to whether this is a good thing or not. And we don't do a very good job of marketing, and because of that, many of the programs that, even the ones I mentioned, have only modest success. They have modest enrollments because of all of this mix of things that we're talking about. So we're still not preparing enough people with this expertise, and this is a continuing issue. So a few observations. There's nothing scientific about these observations. These are just personal kinds of things that seem to be the case anecdotally for programs that I have worked with. The successful programs tend to have strong connections to either research efforts and or to industry partnerships, so that there's benefits for both sides. So if it's connection to research efforts, it means faculty are actually training undergraduate or graduate students in ways that will help them further their research, and that gives them incentive to spend the instructional time to make this work. Or there's industry partnerships where there internships where the industry becomes a placement for the students, might sponsor some financial things. The industry can help convince administrators that this is an important thing for the university to invest in, and so on. So those kinds of things are very important in terms of success of these kinds of interdisciplinary programs. A second thing is to have participating faculty across multiple disciplines. If it's just a few faculty in a couple of disciplines, the program is going to be weaker. It's not going to have the same reach. They won't be promoted across all of the disciplines where it might be relevant, and therefore there won't have enough students. So those institutions that have faculty with expertise across a broad range of disciplines will tend, I think, to be more successful. I think in the future, private sector push for qualified employees is something that will really help with this, as I mentioned earlier with the industry partnerships. I think it's difficult for academics to sort of convince the dean and the provost to go in these new areas, although data science has become very hot and why has it become very hot? Because the private sector is pushing for qualified employees in those areas. The same push hasn't occurred for the more science and some of the engineering disciplines, but that needs to happen in order to get these programs to be more successful. Institutions where there's flexibility in internal financial and appointment arrangements also can do this more easily than those that have typical departmental organizations where all tenure and salary decisions are made at the department level, and efforts to do interdisciplinary things become punished. On the other hand, if you have flexibility in those arrangements, that creates a different incentive structure for faculty and can add to the success of programs. The last thing I want to mention is that one of the things that this chapter could think about in the long run, and one of our long run goals, is to think about possible endorsement by professional societies for the competencies or for certain programs as a way of creating backing for faculty that are trying to make these programs a success at their institutions. And that's something in the long run that I would like the chapter to think about, and think about how to create this sort of endorsement and really take it maybe not just from the chapter level but up to the ACM in general, to think about more broadly as a way of getting more people trained in computational science. So we're to the question and discussion period now. So give me a second to get back to my control screen. And so I'm going to turn it over to David, who's been following questions. I don't know how many there are. If you have other questions, please take a minute to post them now. And David, do we have any to follow up on at this point?
Yeah, there's a question from Salvador Filipponi. Is there any programs in computational linguistics or other social sciences?
There are components of the programs I mentioned in computational linguistics and in economics. I don't know that there are standalone programs. I forgot to go and show you that list of programs. But if you go to the HBC University site that I was on under students, there's a list of both the graduate and undergraduate programs we found, and you'll probably find a couple of those in the social sciences listed there. Most of them otherwise tend to be integrated with these comprehensive programs, like at Ohio State, where there is this minor, but there is a linguistics elective program, and there's also some economics electives related to that. Are there other questions? So we're going to pause here for a few minutes, hoping that some other questions get posted. David is tracking those, so we'll hold on here for a minute. The other things that you could post is if you have questions or suggestions for sort of future presentations, meetings. We got a few of those at the supercomputing meeting, and so while others are posting questions, I might mention some of those. People were also interested in sort of professional development outside of the academia, that people that want to go back and enhance their skills in these areas. So we hope to have several sessions related to those kinds of programs. We also want to begin to engage multiple institutions that are doing these kinds of training to see if we can combine resources and figure out ways of offering a broader range of training that's easily accessible. And David, can you remember some other things that came up at supercomputing that should be part of future agendas?
Actually, while you were talking, we have another question from Brad Berkman. What can we do to get more students interested in such programs? I'm thinking about starting at the high school level. What are your thoughts on that?
Well, Brad is at a very unusual position to be able to start something at the high school level, and that would be terrific to get the idea in the high school, so that when the students come to universities, then that they would look for related programs. So I think that would be very productive. I believe there are a couple of other efforts along those lines. I think there are a few other places trying to teach modeling and simulation kinds of things as part of high school curricula. It's still a difficult thing to market, and until it becomes more mainstream, I think we're facing some resistance. It's not a typical, there are very few places where it's a major. It's not a well-established field yet, so it's going to take some time, I think, to grow the field.
I know during the Birds of a Feather at SC there was another question about certification. Any progress on that?
There are some things underway. The Exceed project is beginning a badging program, which is the start of certification, and we're also working with a number of institutions, both nationally and internationally, that are interested in the same kinds of things. And we hope to make that a subject of some future meetings to help round out, both to advertise at those emerging programs and also get people's views on how they should be organized and what the needs are. So we hope to have that at a future meeting.
And any comments about upcoming events, both for SIGHPC EDU and, of course, other professional HPC conferences, the way of coordinating that?
There are a few things I could mention. There's going to be a pre-event at the SIG CSE conference in March for people to build the Little Fee, which is this miniature version of a parallel computer. We have an NSF grant to award 3 of those systems to 3 institutions that will go through the build and then take them to their home institution and use it to help teach parallel computing concepts. There are a couple of other academic programs that I might mention. There's the Blue Waters Fellowship programs aimed at PhD students in computational science, which is a very generous program that supports PhD students in their research for 1 year and gives them allocation on the Blue Waters system. The Exceed project also has the Exceed Scholars program, which tries to recruit underrepresented groups to participate in a year-long experience, getting exposure to high-performance computing. A lot of these kinds of things, by the way, are announced on the HPC University site. So if you're looking for these opportunities for your students, internships, those kinds of things, I would encourage you to go there, because we're trying to make that a place where we post information about all kinds of opportunities, both for faculty, professionals, and students. And that's where we'll do that, and we'll also try to cross-point to that from the SIG HPC education site.
Have a couple more questions from Chris Gottbraith. Aside from majors and minors, to what degree do you believe that undergraduate and graduate computer science degrees and degrees in disciplines with a long tradition in computational sciences like physics are getting some level of introduction to computational sciences?
That's a good question, Chris. That really varies widely by institution. So even if there isn't a minor in computational science, there are people in physics and chemistry and engineering that are teaching some of these things in their classes. So if you're an engineering major in mechanical engineering, you're very likely going to get an introduction to finite element methods and a number of other things that are related to what engineers will do with computation when they graduate. If you're a major in physics or chemistry, you're likely to get some introduction to chemical modeling or modeling of physical systems or those kinds of things. So you get some exposure, but not the depth that you would get if you took a full minor. So there is that growing. And where these minor programs come from is that they're grown from faculty that are teaching a little bit of this in their disciplinary area, notice that there are colleagues in other disciplines teaching a little bit and want to get their students a bit more depth, and so that's where the minor programs are emerging from.
There's also a question from Dana Brunson. I'm interested in using the possibility of student internship to help market these sorts of classes, but I'm not sure where to begin to learn more about internships.
So there are two things here, Dana. I mean, one is at Ohio State we've sort of done it in two ways. One is we actually have faculty that are deep into research that are applying computational methods, and so students can become an intern for those faculty, working either for pay or even sometimes as volunteers for credit to get involved in those research projects. They often become co-authors of scientific papers. But there are also then connections with local industry or even in the national scene with the national labs and others that offer internships. So for those national things, we do post the opportunities on HBC University, but also if you're going to develop this broadly, you need to develop relationships with your faculty that might have positions that are relevant, or with local industries in your own home state or city that might be interested in having interns that have some of these computational skills.
We have a comment from Salvador about the programs in Europe that we might want to list the Summer of HPC program from Price, and he sent the URL for that.
Great, be glad to do that. As I said, we're not as good at the connections with international institutions, and we're trying to close the loop there as much as we can. Well, David, if that's all the questions, perhaps we can close the meeting, or are there anything else in the queue?
That's all the questions at this time.
Well, then let me thank everyone for joining us today. We appreciate this. I hope this works to connect us, since this is a virtual chapter. If you have other suggestions, either on the technology or topics that you'd like to see again, please feel free to write us. Our email addresses are on the SIGHPC education site. And just to before I close, let me go back to screen share and show you these last couple things in closing. So here we are at the HBC University site, and if I go under students, you can see that there are, here's the list of the undergraduate programs, and for each one then we have the institution, we have a link to their website, and we have them in order of, I think, domestic and then international. We also have a place to submit additional programs, so you can submit those so we get them on the list. And similarly for graduate programs, there's a list here. And then if I go, let me just go to one other places. So here is the chapter website. So aside from membership, our bylaws, under the events thing, you can see the tag links to our meetings today. Here's my presentation slides. Here are the slides from our meeting at the supercomputing meeting. This is where we'll post things. So if you miss the email for the future meetings, you can always come here, and we will post the links to future meetings on this site, and we'll begin to build up cross links to other kinds of things as well. So with that, I think I'll close the meeting, and thank you all for joining, and I hope we'll have another meeting in January. We'll post notices of that as soon as we have that arranged. So thank you all again, and hope to talk to you soon.
Thanks, Steve.
Okay, bye-bye.